Good morning, everyone. Dr. Pete here for my 7 a.m. Friday presentation, which hopefully after today is going to become a regular thing again. I have published on YouTube and I've gone live on at least one event to talk about the polyol fructose uric acid metabolism and its relevance to operating as a central driver of most, if not all, metabolic diseases. I also spoke at a recent conference, the Collaborative Science Conference in Las Vegas, the conference put together by Dave Feldman. And I promised that I would do a series of videos that would simplify the biochemistry of this, because one of the criticisms that I've gotten over the last couple of years is that I'm too technical, that I rely on talking about the hardcore science of metabolic disease, making it above over the heads of the people that listen to me. And so I'm responding to that. And these Friday mornings are going to be devoted to trying to disseminate that and educate my fellow people about how this biochemistry works and what we can do to be healthier. And that's going to include some sessions where we talk about the term health. But this morning, I am going back and talking about polyol fructose uric acid metabolism in more basic terms and what my thoughts are about the physiology of humans in regard to our metabolism. So let's go ahead and get started. And today's topic really is special because there's a term that is used by the cancer specialists, especially Seyfried, that all cancers are metabolic. That's number one. They even if they have a genetic component, there is also a significant metabolic component, and that this metabolic component is defined as mitochondrial insufficiency. And the reason why I want to talk about this morning is because I have made the assertion that we know the core biochemistry that's driving most, if not all, metabolic diseases, including cancer. And fundamentally, why is because when we open polyol fructose uric acid metabolism, this drives a change in the mitochondrial function, which is, in fact, a mitochondrial insufficiency. And therefore, this metabolism can drive most, if not all, metabolic diseases, but also at the core of it, cancer. So we're going to talk about polyol fructose uric acid metabolism once again this morning in more general terms. So coming back to what I talked about last week, one needs to recognize that when they eat, we have glucose. It doesn't matter what type of carbohydrate that you eat. It's going to be converted in one way or another into glucose when it gets into the circulatory system. And then depending on how it comes in, fructose can also be part of that, right? Any added sugar, for example, like sucrose, is 1 part glucose and 1 part fructose. And so when that crosses the intestinal barrier, it's going to be, the sucrose is going to be converted into glucose and fructose. We're talking about this from the point of view of glucose, and I'm doing this very deliberately because one of the pushbacks or the resistance to this idea that fructose uric acid is a central driver of most, if not all, metabolic diseases is that, or the contention that this pathway is only open when somebody ingests fructose, like fructose sweetened drinks, something along those lines. And this is not true when you consider the polyol pathway. And I've addressed that issue in the last couple of technical videos that I've put on my YouTube channel. Last week, I did a live episode where I readdressed that in simpler terms. So the whole point is that fructose uric acid is as much about the glucose as it is about the fructose. And this is an important consideration because humans, from an evolutionary point of view, depended on this metabolism to very rapidly store fat and glycogen to stimulate our immune system and to alter our nitric oxide signaling in order to manipulate our blood pressure, right? To make sure that nutrients got everywhere, went or arrived at their destinations everywhere that they were needed, right? In particular, this was very important for brain function, for example, because the brain utilizes so much of the glucose energy coming in. And, functionally, fructose uric acid metabolism, when it's activated, is directing a lot of that signaling, including even insulin, right? And we all, in this space, we hear about insulin all the time. And I feel like I've been almost alone to ask the question about, okay, what's underneath the insulin, right? What's driving this shift? And fructose uric acid metabolism explains that actually very eloquently. So basically, when we think about this in terms of glucose, when glucose comes into the liver, it has a choice about which direction it's going to go. There's a fork in the road, and I'm showing that here on this slide. And depending on which way the glucose goes, if it's going to be processed into storage in the form of fat and glycogen with the elevation of systemic inflammation and also the nitric oxide signaling, or whether or not it goes to the right in this slide and progresses through glycolysis with the glycolytic connections to the mitochondria through pyruvate and lactate, depends on the concentration of glucose. And sitting at the head of this fork is the front end of what Johnson has characterized as the survival switch. This is the front end of it. There's actually a cascade of switches that occur when this metabolism gets opened. The front end of this switch is characterized, I contend, by 4 enzymes. The front 2 that are super important here are glucokinase and aldose reductase. And both of these enzymes are expressed under elevated concentrations of glucose. Under concentrations of glucose that are low, specifically under 5 millimolar intracellular glucose, which is under 90 mg per deciliter, then the cell of the liver, if you will, which is where these nutrients first arrive through the portal circulation, right? They come in across the intestinal barrier into the portal circulation. They go by and interact with the pancreas. And then we have pancreatic signaling. Those nutrients make their way in the portal circulation directly to the liver. And the liver really is the captain of all this stuff because those nutrients are all arriving there. And then the distribution happens, or the liver effects and the signaling and the glucose that's not processed by the liver and so on are then pushed into the peripheral circulation to make their way to all of the rest of our organs, the adipose tissue, the muscle, kidney, brain, and so on. So when we have low glucose conditions under 5 millimolar, under 90 mg per deciliter, then the liver is going to choose the right fork here. And we are I'm going to define this morning, in a burning state, which for a human is the most healthy state to be in, besides the combination of exercise. And I'll come to that momentarily or down the road here in a couple of minutes. The burning state. And the reason why this is the healthiest state to be in overall, along with the exercise, is because of the flow of electrons. They enter at point A and they exit point B in the form of H2O and CO2. And what do we get out of the deal? We maximize the amount of adenosine triphosphate, ATP, that's produced. And that's arguably, along with other molecules, but arguably ATP is the currency that the cell uses to pay for the things that we need to do. As simple as our brain and the thinking that you do in your brain, that costs energy, right? Anytime you get up out of your seat and you're walking around and you're utilizing your muscles, you're burning ATP. And so we need the production of ATP in order to burn energy to do the things that a human does. Anything that involves activity, for example. Now, when we let the glucose rise like it does after a meal, and that glucose rises above a certain threshold, and arguably we don't know exactly what that threshold is. Some people have come back to me in comments and said, well, you're arguing that when the glucose rises above 90 mg per deciliter, that this is where this transition happens. And Dr. Pete, that sounds really low. That threshold sounds really low. And yeah, it does. But the reason why I choose this number as a starting point in the discussion is because that point at 5 millimolar, rising above 5 to about 9 millimolar, is where both glucokinase and aldose reductase, and aldose reductase is crucial here to talk about because it's the enzyme that is sitting at the head of the polyol pathway and catalyzes the conversion of glucose to sorbitol. And then in the polyol pathway, the sorbitol is converted into endogenous fructose. So the liver is producing its own fructose. And aldose reductase is sitting at the head of that. And we know from very high quality research that aldose reductase is activated under the same glucose conditions as glucokinase. So there has to be a relationship here. And what the actual threshold is requires more high quality research that looks inside the cell at what is actually going on to make the choice between shifting towards burning and shifting towards the storage state, which, as you'll see, lands at a change in function of the mitochondria. And that's where all this business, when it's done chronically, every single day, day in, day out, week after week, that's how a 60-year-old, that would be me, right? I'm 65 now, but when I was 60, that's how I got diagnosed with prediabetes, because it took 6 decades of eating this way with the pressure towards dysfunction that finally caused me to be sick, right? And we're seeing these, we're seeing an elevation in chronic metabolic diseases, not only at this seems like this pinnacle age of 60 moving forward from that, but also into our younger generations, because they're eating this way at younger and younger ages. Whereas as adults that are over 60, we started down this road at a later time in our life. All right. And that's why with the younger age group, I'm talking about the 30-somethings that are having children and whatnot. These guys are also showing up with chronic metabolic diseases now at a higher rate than we did, because they've been eating this way longer. Probably started with the mother when they were in the womb, or the mother was eating this way already, right? And then we had a baby in the womb, basically, who was eating this way because the mother was eating that way, all right? Anyway, that's sort of the backstory here. So let's move forward. This just shows that when glucose is low, the survival switch is closed, and shown here by the gate on the left. And you can see the glucose molecules are moving down into committed glycolysis with the output of pyruvate and lactate that get funneled into the mitochondria, and then essentially, long story short, converted into ATP. And I've already described that. However, when the glucose rises, both glucokinase and aldose reductase are activated, and glycolysis at the level of the phosphofructokinase 1 reaction. This is really the committed step to glycolysis is inhibited. And now the glucose is funneled to the left. And in terms of the glucose, it arrives at, through polyol, it arrives at this enzymatic reaction that's catalyzed by fructokinase, which is a trapdoor enzyme. It's once it starts operating on the fructose that's being produced in the liver, this is an irreversible reaction with, sorry to say this, but with thermodynamics that are highly favorable. That means that everything that arrives at fructokinase, all that endogenous fructose is just immediately converted into product, fructose 1-phosphate. And we have that sudden acute decline in cellular ATP with the sudden acute decline in phosphate. We have the activation of AMP deaminase with the sudden acute rise in uric acid. And uric acid is a signaling molecule that, among a number of functions, causes a change in function at the level of mitochondria. And remember, the purpose of this pathway, this is the way that humans are able to rapidly store fat, rapidly store glycogen, produce glycogen, that's the storage form of glucose, stimulate our immune system, and alter our nitric oxide signaling so that we can push nutrients where they need to go. The main thing I'm going to talk about this morning is the fact that once that uric acid has a sudden acute rise in the liver, which happens in everybody under these conditions, that we change the function of the mitochondria. Now, what exactly happens at the level of the mitochondria? And I'm going to be very pragmatic with this, and I'm going to walk through what exactly happens here. And so I'm going to look at my notes because I don't want to forget anything. So first and foremost, there is an actual change in morphology. The mitochondria become smaller, they become fragmented, and imaging studies show under these conditions that there is an alteration in the inner membranes. And anyone who knows about mitochondrial function and oxyphos, right, the movement of these electrons that are driving the production of ATP, if we're changing or altering the structure, the transient structure of those membranes, then we are altering oxyphos. And there's data for this. We know that, among other things, lactate, for example, drives a change in composition of cardiolipin, and cardiolipin is known to regulate oxyphos. Boom, right? And that's not the only effect, right? There are others here. We have an inhibition of the TCA cycle because uric acid, in a uric acid dependent way, we downregulate aconitase, which is an enzyme that catalyzes the transition of citrate to isocitrate. This causes citrate to pool in the mitochondria. It's pushed back out into the cytoplasm, where the citrate does two things. One, it initiates de novo lipogenesis, the production of fat right in the liver. And secondly, it feeds back and, along with lactate, inhibits phosphofructokinase 1, which is a key enzyme in the very early stages of glycolysis that drives an irreversible commitment to the glycolytic pathway. And the citrate is feeding back and inhibiting that enzyme. So we're favoring, remember that initial slide that I showed, the first two initial slides, we're inhibiting glycolysis, and we have opened fructose uric acid metabolism, so the glucose is being funneled into fructose uric acid metabolism. At the same time that fructose uric acid metabolism is open and we have this shift of citrate into the cytoplasm with the activation of de novo lipogenesis, we also activate carbohydrate response element binding protein. That's a mouthful. We are also activating carbohydrate response element binding protein, which is translocated from the cytoplasm into the nucleus, where it specifically activates the genes of de novo lipogenesis, including ATP citrate lyase, acetyl-CoA carboxylase, fatty acid synthase, and steroyl-CoA desaturase 1. We have the uric acid dependent inhibition of enonyl hydratase. This is an important enzyme that is required for the beta oxidation, the oxidation of fatty acids in the matrix of the mitochondria in order to generate ATP from the burning of fat. Back in the cytoplasm, we have the pooling of malonyl-CoA because of the active de novo lipogenesis. And malonyl-CoA, along with lactate, here's another lactate effect, feeds back and inhibits the ability of the mitochondria to transport fat from the cytoplasm of the liver cell into the mitochondria, where normally it would be burned by beta oxidation to produce ATP. We have the fructose, uric acid, and uric acid derived induction of the hypoxia protein called HIF1 alpha, which in concert with the uric acid downregulates urea cycle enzymes. We have the induction of the hormone FGF21, which is known to alter the intake of carbohydrate. We also have the induction of JNK1 and IL-1 beta, along with the activation of the NLRP3 inflammasome. This is where we're seeing the induction of systemic inflammation, right? Going back to what I said earlier about the activation of systemic inflammation to stimulate the immune system. And lastly, because of the going back to the front end of this talk where we talked about the sudden acute decline in ATP with the sudden acute decline in phosphate, we had the sudden activation of, or the upregulation in AMP deaminase, which drives the downregulation of AMP kinase. One of the functions of AMP kinase, for example, is to drive the beta oxidation of fatty acids. So we have here, and this list was not exhaustive, we have here a change in function of the mitochondria when we open fructose uric acid metabolism. Now, when you sit back and you look at this data overall, which is coming from hundreds of publications of high quality, non-associational type of research. I'm talking, this is like cellular, in vitro, in vivo animal studies, and also human clinical studies. When we activate fructose uric acid metabolism, this suggests that we actually have a change in physiological state at the level of the human biology. It's a change in state. And I'm showing that here. I'm showing 3 states. And I'm arguing that humans exist in metabolic states. This isn't the idea like when people get into a classroom where they're learning about biochemistry, if that happens, for example, at the university level, they're taught all of this biochemistry is individual pathways. And the professor will go on, well, when we have glucose, it's processed by glycolysis and then, yada, yada, into the mitochondria. When we process fat, this is how the fat is processed. And what I'm arguing is that none of these pathways are operating in isolation. We actually have shifts in state. And when we think about an ancestral human, they were only shifting into this polyol fructose uric acid state of affairs, if you will, with the change in function at the mitochondria intermittently, right? When you think about what their life was like, they spent most of their time in states of exercise and in burning. And I'm showing the burning state here in white. I'm showing the exercise state in pink. And the exercise state is pink because when you access the exercise state, it matters whether or not you spend most of your time in a burning state like we do in low carb, or whether you're spending most of your time in the red state, which I'm showing over there on the right. And that illustration is larger because basically most people are eating 5 to 6 meals a day, and the proportion of the molecules that open fructose uric acid metabolism are very high, right? The fructose content, or excuse me, the carbohydrate content at the lowest possible incoming amount is 55%. This is what the medical establishment says that the standard American load is. I disagree with that because I've been doing this for 6 years now. And I actively work with people who are metabolically seriously sick, type 2 diabetes, the obesity thing, cardiovascular disease, stage 4 kidney disease. I've worked with all those people in a coaching capacity, along with the overseen by a medical doctor, to reverse those conditions. And it doesn't matter what the individual on day one, when we're starting out, they all are eating, 5 to 6 meals a day and significantly more carbohydrate than number one, they're willing to admit. And number two, what the actual value is. The consequence of this is that they spend most of the day in this metabolically, which eventually becomes a dysfunctional state, right? They spend most of their time in the red state, and down the road, this driver is how they end up with these metabolic diseases, including cancer. And this metabolic state that I've talked about at the level of the mitochondria mirrors the state of the mitochondria, in which a lot of cancer specialists now are beginning to admit is a main characteristic of the mitochondria in people that suffer from cancer. So this is a serious thing for any of us who are eating this way over decades. Now, when we start to talk about, all right, what do we do in order to shift our health towards a parameter that avoids these metabolic diseases, can reverse these metabolic diseases, or at least put them into remission. And that shift is to be in the burning state most of the time, and to also accompany that with exercise. Because when you look at our ancestors and you ask, all right, what proportion of the day were they, what proportion of the day did they spend in the burning mode, in the exercise mode, versus when they were bringing calories in? And they were in this activated state intermittently. They were not in it in a chronic fashion like we are today. We spent back then most of the time with a very high workload. And anyone who's had any experience with this, I have had some when I've talked about this before, when I was in my late teens and early 20s, I taught survival in the mountains. And I know what it's like to have to go out every single day and get food. And sometimes we were lucky to have anything at all on any given day, and then when you did get it, you ate it. So we spent quite a bit less time in the red state, if at all. All right. This is an important concept because it basically suggests to us a way of life that keeps us out of the red state, maximizes our time in the burning state, which is a significant, I'm going to use this word now. We will, in other presentations, talk about this concept of health, but being in the burning state and the exercise state is clearly healthy. One more healthy than being in the red state all the time. And the reason that my exercise state is pink is to indicate or acknowledge the fact that when you go from the burning state into the exercise state, that state is going to look different to somebody who spends most of their time in the burning state, in contrast to somebody who spends most of their time in the red state, and then they go to the gym and they exercise. These two states are different. The two exercise states are different. depending on where they come from. And this is because of the chronic gene regulation and activation and so on that's going on with somebody in the red state by comparison with somebody who's in the burning state most of the time. And you can see this when you look at high quality biochemical work that's done on athletes that are put in a low carb environment for an adequate amount of time versus shifting them into the standard American diet for an adequate amount of time, and then looking at the biochemical parameters that they express, like VO2 max. And for example, VO2 max in a red state athlete is around 65%, whereas the VO2 max, this is just one little criteria I'm talking about, whereas the VO2 max for somebody who is shifted into the exercise state from the white mode, right, from a mode that comes from burning and living in a low carb state, the VO2 max is about 85%. So it turns out, if you look at this data significantly, we are more metabolically flexible than somebody who lives in the red state and then goes and exercises. We access fat burning even at the highest levels of VO2 max. So living in this world where the carbohydrate content dominates the plate, it's shocking. You know, having done this now for 6 years, I can't help whenever I'm in a social environment where I'm looking around at what people are eating. It's even as those guys talk about how healthy they are and the fact that they're eating a healthy diet, when you look at their plate and you see the literal disproportion of what's sitting there, the carbohydrate, which is dominated by easily refinable carbs, right, that are easily converted into glucose on their plate, it's shocking. And when you think about how that diet, how that input is affecting them over the years, well, for someone like my age, sitting around that table is an example of cardiovascular disease, the obesity, all of these statistics are sitting right there, and you can clearly see them sitting around you, right? If just thinking about this differently, turning this on their head, and I'll come to that in a second. But anyway, the point of this slide was to emphasize the fact that when you are living in this lifestyle, every single time we change the function of the mitochondria into this mitochondrial insufficiency because we're not burning anymore, right? This eventually is the reason for this escalation in metabolic diseases that we see, the type 2 diabetes, the obesity, all of this stuff, the cardiovascular disease, the coronary artery disease that we see, and also this range of cancers that are also on the uptick, right? This just reiterates that last comment that I made. There's really strong, I don't like talking about associational data, but the associational data for activation of fructose uric acid metabolism and the generation of metabolic disease is quite strong. Hundreds of publications that come back and show the same thing over and over and over again. And all I did at the bottom of this, anyone who listens to me, was I interjected mitochondrial insufficiency, because that's what's going on. All of this comes back to the mitochondria. So what I want you to do, I'm going to ask you to do, is just sit back for 1 minute and think about when this stuff really took off. And that happened when the nutritional guidelines were published in 1983. And what people don't understand about this is that there was a governmental committee that happened at the Senate level that marched various exercises by that marched a number of experts by them, which did include scientists who said, hey, you guys, do not come out advocating for a low-fat, high-carb diet as the way to be healthy. Because if you do that, you're doing it without the data that actually says this is so. And that turns out to be true. And the purpose of this presentation is not to walk all the way back through that. There's a ton of influencers who talk about this out there all the time. And I don't want to attempt to do that here. What I do want to point out is that they did hear from experts who had very high quality biochemical evidence that was not associational, that was in contrast to what they were promoting. And they didn't listen. And not only that, but as a consequence of this, some of those guys had their careers ruined. They lost their grants. Some of them stayed in the research arena, but they changed what they were studying in order to get grant funding. Basically they were cut off at the legs. So what's the point of this slide? The point here is to ask you to do this, to consider for a moment whether or not, if we had nutritional guidelines actually supporting what the science said, what that would look like. And what that would look like is shown here to my right. I'm always getting my directions wrong. And you can see that this food pyramid looks completely different than the one that our whole food industry was built up around. Because if this was the way that we were eating uniformly throughout our population, and this had gotten started over 40 years ago when the nutritional guidelines, the way they stand right now, had come out, we would be looking at a completely different thing than what we're looking at. More than likely, at 60 years old, I would not have been pre-diabetic, nor would I have been suffering from gout, if the actual data had arrived where really it should have arrived. All right. Now, how do we put this into a practical thing? And I've shown this slide a lot in my presentations. You basically, what you want to do is eliminate the drivers of fructose uric acid metabolism, and that includes all of the added sugar, and not having hyperglycemic meals. Now, I'm defining hyperglycemia different than the medical establishment now. I'm defining it as the concentration of glucose on an intracellular level that is capable of activating polyl-fructose uric acid metabolism. We need to make that metabolism, that open doorway, for example, we need to close it off and only use it intermittently. So like if you're sitting there right now and you're younger and you're wondering, well, how can I eat this more metabolically healthy? Don't activate that pathway 5 or 6 times a day. It's far more healthy to move to a situation where you're eating 2, maybe 3 meals a day, and you bring the carbs down. I mean, that's the truth of the matter. The carbs should come down. And when you bring them down, you will immediately start to see the benefits of this, right? Because your weight's going to come down. This is one of the things that is the saddest story that is really at one of the forefronts of our media right now, and that's the obesity crisis. And we don't see any discussion about this issue at all, anywhere. There was just the Oprah special that came out. Maybe some of you saw it. And they marched all kinds of experts across that stage. They had doctors there that are prescribing Ozempic that actually work for the pharmaceutical companies that produce these drugs. How much more bias do you want with this? Just changing to this way of eating brings weight down at nearly the same percentage and rate of percentage drop as utilizing those drugs. And it deals with the underlying cause, right? Those drugs don't deal with the underlying cause, right? They don't. So as soon as those people go off those drugs, they gain the weight back. Why? Because they didn't change the way they were eating. And so knowledge of this biochemistry, we can use it to improve our quote unquote health, right? Just know I'm using that word differently than most other people use it, right? For me, when I use that term, I mean a whole group of aspects come into play here for me. Not only not eating this way 5 to 6 times a day, right? But focusing on low carb, focusing on being in the red state only in an intermittent fashion, right? And then having as other components of my life the exercise component, which I will talk about in a separate presentation, but that involves a number of factors, not just going out and walking 30 minutes a day, 3 days a week, which I actually heard about that last night in a neighborhood meeting. Somebody stood up and said, well, my doctor said I should be walking 30 minutes, 3 days a week. Yeah. Okay. If you're doing that, that's a really, really good thing. But our exercise program should be much more extensive than that. So I think I'm going to go ahead and move on. I have shown this slide quite a bit. And that brings me really to the close of this discussion. So what have I learned from this biochemistry? I have learned that it is a good idea for somebody to think about cutting the carbs down to a proportionality that is more realistic. And I know that we hear a lot about this out there by other influencers that eat the way our ancestors did. And so am I saying that? I kind of am, right? I'm saying that we can learn from that. And there's a lot of data behind this. When you look at early studies that were done where scientists went out and looked at populations that were isolated from people that were eating the Western diet, you just don't find the cardiovascular disease, the obesity problems, the diabetes, and you don't see the cancers either. You know, it's only when you look back at the way that we've eaten now for the last couple hundred years, that those of us in the urban environments, to just make a distinguishing factor from an ancestral population that's isolated. We have all of that stuff in there. We have all the chronic metabolic diseases, and they don't. So what can we learn from that? And what I'm saying is in the context of somebody who is already metabolically healthy. And there are discussions about that too. What does that mean exactly? But let's just, for the sake of argument, say we're dealing with somebody who's metabolically healthy, then switch the proportionality around. Prioritize high quality meat with fat on it, and the fat that also is used to cook with, right, in your life, and deprioritize the carbohydrate. And think about meal timing, right? This idea that you're eating from the time you get up, and that includes the coffee that might have sugar in it, going to Starbucks and getting, oh my God, these combined drinks that have all the sugar in there, and then eating this way basically all day long. Here's an exercise that you can use to really objectively ascertain what your lifestyle is like eating wise. Take a picture of it. Every time you're going to put something in your mouth, that particular day you're going to do this, take a picture of it. And the next day, roll through those pictures and take an objective look at the level of carbohydrate, all told, that is in there. And I think what you're going to see is shocking. It is shocking. Flip it. That's the thing to do. Flip it and make it the other way around. And think about the meal timing and maybe only having carbohydrate on that plate at one time out of the entire day, or legitimately only eat a small amount of it, and watch and see what happens. Try it for 3 months and see what happens to you. I can guarantee you your weight's going to come down unless you're cheating, right? And that's, again, like being very objective about what you see and what you eat off that plate. All right. Anyway, that's what I got for you today. I'll see you next week.